So hello students, welcome back. In a last video, we had discussed about how to obtain the expressions for VDC as well as VRMS for a half-wave rectifier circuit. Okay, so today let us look at how to obtain the same expressions, that is VDC and VRMS for a full-wave rectifier circuit. Okay, well, if you just observe the output waveform for a full wave rectifier circuit, this is how it looks like. Okay, so the working of a full wave rectifier we had already seen in one of our previous video sessions. Okay, so today let us try to obtain the VDC and then the VRMS expressions for a full wave rectifier circuit. So to start with, VDC of a full wave rectifier can be written as VDC equal to, now uh, because the output waveform is repeating at every t by 2 intervals. Okay, so if I just want to write the expression, I can write it in this way: 1 upon t by 2 integration of 0 to t by 2 Vm sine omega of t dt. Okay, so now this is the way I can write it. Why t by 2? Because for after every t by 2, okay, the signal is just going on repeating, so we'll have to take the mean as t by 2. Now if we just solve it, we are going to get, because Vm is a constant, let me take it outside. Okay, so if I take 2 above, it becomes 2 Vm upon t integration of 0 to t by 2 sine omega t dt. Okay, so 2 Vm upon t, let me keep it as it is. Now integration of sine omega of t is minus cos omega t upon omega, so I'll just write this minus here. So it is cos omega of t upon omega limits 0 to t by 2. So minus 2 Vm upon t. Let me just substitute it. Omega is 2 pi by t. So 1 upon 2 pi by t cos of 2 pi by t multiplied by t by 2 minus of cos omega 0, which is cos of 0. Okay, so if I further simplify, t gets cancelled, 2 gets cancelled, I'll be getting minus Vm upon pi, and within the brackets t gets cancelled, 2 gets cancelled, so cos of pi is minus 1 minus cos of 0 is 1, so it is 1. So if I further simplify it, I'll be getting 2 Vm upon pi. Okay, so this is the expression for VDC, or the average DC voltage of a full wave rectifier circuit. Okay, so roughly if we just want to represent it on the output waveform, well, this is somewhere we can represent that VDC value for a full wave rectifier circuit. Okay. Okay, so to start with, VRMS for a full wave rectifier. So if I write the expressions again, considering the waveforms of a full wave rectifier, I can write it as 1 upon, okay, so since it is root mean square, RMS stands for root mean square. Okay, so I'll have to take the root first, then mean. So now while considering the mean, okay, see here, because this particular waveform is keeping on repeating for every t by 2 period, okay, for every t by 2 period, so in the integral I can also consider it as 1 upon t by 2, 1 upon t by 2 integration 0 to t by 2, then Vm square sine square omega of t dt. Okay, so that's the expression for root mean square. Now just to simplify, I'm considering VRMS square so that the square root can be eliminated, and then later I'll be taking the square root of it. So it is just 1 upon t by 2 integration of 0 to t by 2 Vm square sine square omega of t dt. Okay, fine. Now if I simplify it further, it will be taking Vm square outside the integral, and t by 2, if it goes up it becomes 2 Vm square upon t. Now I can express sine square omega of t with respect to integral formulas as 1 minus cos 2 omega t divided by 2. Okay, so I can mention it in this way, taking the integral 0 to t by 2 dt. Okay, so simplifying it further, I'll be getting 2 gets cancelled, so it is Vm square upon t. Now performing integration, so integration of 1 with respect to dt is t minus, okay, integration of cos 2 omega of t is sine 2 omega of t divided by 2 omega, again considering the limits 0 to t by 2. Okay, so now if I just substitute, I'll be getting, if I solve Vm square upon t, okay, substituting the limits, it will be t by 2 minus of 0 is t by 2 minus 1 upon 2 omega, so sine 2 omega is 2 pi by t, substituting t by 2 minus of sine 2 omega 0. Okay, so if we closely observe here, 2 gets cancelled, t gets cancelled, we are left with sine of 2 pi. Okay, so sine of 2 pi is 0 and sine of 0 is also 0. So similar to the case of a half wave rectifier, these two terms also get cancelled, okay, because they are equal to 0. Okay, so the entire term becomes 0. So what are we left with? Here again t gets cancelled, so I am left with Vm square upon 2. Now this is V square RMS. Okay, but we want VRMS, so therefore VRMS is equal to taking the square root of Vm square upon 2, which is Vm upon square root of 2. So that is the expression for VRMS. Okay, fine. So I think students have understood how to find the expressions for the DC voltage and then the RMS voltage of a full wave rectifier circuit. Okay. All right. So thank you very much.